A 2,000-year-old concrete pier stands unbroken in the sea. Modern versions crumble in mere decades. This is not a story of lost strength, but of a forgotten science. By the end of this investigation, you will understand the precise chemical secret that let Roman harbors outlast empires. We will uncover how seawater, the very force that destroys our structures, became the ancient builders' greatest ally. What does true resilience look like when it is built into the very fabric of a material? The most compelling proof of this ancient mastery is not in a laboratory, but in the sea itself. Off the coast of modern Israel, in the harbor of Caesarea Maritima, lie the silent witnesses, built by Herod the Great to honor the Roman Emperor Augustus. This was once a bustling gateway to the Eastern Empire. Its most critical component was a series of massive concrete breakwaters, submerged arms stretching hundreds of feet into the Mediterranean. Their job was to absorb the relentless fury of the sea, to create a calm haven for ships. For over 2,000 years, they have done exactly that. While the grand city above changed hands through conquests and fell into ruin, these underwater foundations have not budged. Wave after wave, storm after storm, they stand intact, their surfaces now home to corals and marine life, yet structurally as sound as the day they were poured. Travel to the heart of the empire, to Portus, the great maritime hub of ancient Rome near Ostia. Here, the concrete piers that once birthed the grain ships that fed 1 million people still project from the shoreline. They have faced 2 millennia of tidal scour, of saltwater saturation, of every corrosive force we know destroys modern concrete, and they are not merely crumbling relics. They are coherent, solid masses. The scale of this achievement is almost incomprehensible. We are not looking at a small, sheltered artifact. We are looking at the engineered backbone of an empire's economy, designed for constant, brutal punishment, and it has performed its duty flawlessly for centuries longer than anyone could have dreamed. These structures are not just old, they are actively, defiantly durable, asking us a silent but persistent question. What did they know that we, for so long, forgot? This is the stark reality of modern engineering. To understand the Roman achievement, we must first confront our own material's greatest weakness. Today's concrete relies on a binder called Portland cement, a product of intense industrial heat that creates a rigid, brittle matrix. When this concrete is used in harbors, seawalls, or piers, it enters a hostile world. Salt water is not just wet, it is chemically aggressive. It carries dissolved sulfates that slowly infiltrate the material, reacting with certain compounds inside to form new, expanding crystals. This internal pressure is like a silent, relentless force, creating microscopic cracks from within. But the true Achilles heel lies in the steel we add for strength. Reinforced concrete is a marriage of 2 materials, and seawater seeks to divorce them violently. Chloride ions from the salt penetrate the concrete, eventually reaching the steel rebar and initiating corrosion. Rust forms and rust expands, occupying far more volume than the original steel. This expansion exerts tremendous outward pressure, causing the concrete to crack and violently spall off in chunks. The process is a predictable, tragic decay. A modern marine structure designed with our best knowledge often faces significant repairs within 50 years and complete failure not long after. It is a race against chemistry we are steadily losing, so the puzzle deepens. The Romans built these immortal harbors without any steel reinforcement at all. Their concrete was mass poured into wooden forms right in the tide. It should have been a recipe for instant disintegration, yet it did the opposite. It grew stronger. This presents us with a beautiful paradox. Our modern method, with all its calculated strength, introduces a fatal flaw. Their ancient method, seemingly primitive, avoided that flaw entirely and unlocked a hidden pathway to longevity. The question is no longer just what they put in, but what brilliant chemical pathway did they set in motion that we accidentally closed off? The answer to this paradox lies not in a single magic ingredient, but in a specific, intentional recipe. Fortunately for us, the Romans were meticulous record keepers. Our clearest window into their methods comes from the architect and engineer Vitruvius, who lived during the reign of Augustus. In his 10-volume work titled De Architectura, essentially the ancient world's manual of engineering, he lays out the formula for what they called opus caementicium. This was not a vague art, it was a precise technology. The first and most famous component was a special volcanic ash known as pozzolana, named for the town of Pozzuoli near Mount Vesuvius where it was extensively mined. This wasn't just any dirt, it was ash from explosive eruptions finely ground and packed with reactive silica. The second ingredient was lime, produced by burning limestone in kilns to create a highly caustic powder. When mixed with water, this lime becomes a putty. The third element was the aggregate or caementor. This was the coarse material that gave the concrete its bulk and strength, typically chunks of volcanic rock or broken bricks. The process was straightforward. Builders would construct wooden forms in the desired shape, often right in the water for harbor works. They would layer in the caementor, the rubble, and then pour over it a mortar made from the pozzolana ash and lime slaked with seawater. It hardened not in a controlled factory, but in the dynamic, salty environment of the Mediterranean itself. Notice what is profoundly absent from this list. There is no Portland cement, a 19th century invention. There is no steel rebar of any kind. There are no complex chemical admixtures, just three simple, earthy materials combined with salt water and time. For centuries, modern engineers looked at this recipe and saw a primitive precursor to their own superior product. The assumption was that Roman concrete was simply a weaker, slower version of what we make today. But the enduring structures in the sea told a different story, one that suggested we had misunderstood the fundamental chemistry at play. If their simple mixture was so inferior, why did it last while ours crumbled? The secret had to be in how those ingredients talked to each other and to the sea across centuries. For generations, the role of lime in this ancient recipe seemed straightforward. To make Roman concrete, you start with limestone. This common rock, formed from the compressed remains of ancient marine life, is primarily calcium carbonate. The Romans would heat it in a kiln to incredibly high temperatures, a process called calcination. This intense heat drives off carbon dioxide, leaving behind a highly reactive, caustic powder known as quicklime or calcium oxide. Quicklime is a dangerous substance on its own. It reacts violently with moisture, releasing heat that can cause severe burns, so the next step was crucial. Builders would carefully slake this quicklime by mixing it with water. This chemical reaction produces heat and transforms the powder into a smooth, workable paste called lime putty or calcium hydroxide. This thick, white putty was the glue of the ancient world, used for everything from plastering walls to binding mortar. In the traditional view of Roman concrete, this lime putty was the sole binder. The thinking was simple. You mix the reactive lime putty with the volcanic ash and aggregates, pour it into place, and as it dries, it slowly reabsorbs carbon dioxide from the air. This process, called carbonation, turns the calcium hydroxide back into solid calcium carbonate, essentially recreating the original limestone and hardening the mix. This model made perfect sense. It was a neat, closed chemical loop that explained how the concrete set. It also, however, suggested a fundamental weakness. If the hardening depended on absorbing carbon dioxide from the air, then the interior of a massive harbor block, submerged and sealed off from the atmosphere, should never fully cure. It should remain a soft, weak core vulnerable to erosion, yet the opposite was true. The most durable, solid parts of the Roman piers are their submerged hearts. This glaring contradiction meant the traditional model was incomplete. The lime was doing something far more interesting than just waiting to turn back into stone. A hidden reaction was taking place, one that did not need the air at all, but instead found a powerful partner in the one element every engineer since has tried to keep out. The missing chemical partner was waiting in the ash. That fine, gray powder from the slopes of Vesuvius was far more than just a filler. Pozzolana is a volcanic glass, rich in aluminosilicates, minerals built from aluminum, silicon, and oxygen. In its raw, dusty state, it is inert and stable, but introduce it to water and, crucially, to the highly alkaline environment created by the lime putty, and a profound transformation begins. This is the pozzolanic reaction, the silent, slow-burning engine of Roman durability. When the calcium hydroxide from the lime meets the silica and alumina in the ash, in the presence of water, they do not simply sit together. They engage in a complex chemical dance. The high pH of the lime solution acts as a key, dissolving the glassy surfaces of the ash particles. Once liberated, these silica and alumina molecules eagerly link up with calcium and water molecules from the lime. The result is the formation of new, incredibly stable crystals. The most important of these is a calcium-aluminum silicate hydrate, often called CaSH for short. Think of it as a microscopic, interlocking web of needles and plates. This is not a single event that happens quickly and stops. The pozzolanic reaction is a process that can continue for decades, even centuries, as long as moisture is present and unreacted ash remains. It is a form of self-healing. If a tiny crack forms, allowing new water to seep in, the reaction can kick off again in that localized area, forming fresh CaSH crystals that gradually fill the gap and stitch the material back together. This is why Roman concrete does not just resist the sea, it incorporates it. The seawater is not an attacking force, it is a necessary reactant, the perpetual moisture source that keeps this long-term chemical conversation alive. So the traditional model was turned on its head. The lime was not there just to carbonate. Its primary role was to create the highly alkaline broth that would unlock the potential of the volcanic ash, initiating a reaction that built strength from the inside out for generations. But this still left one final, glaring mystery. If this ash was so powerful, why did modern engineers who knew about pozzolans not simply replicate it? The answer lay in a specific, overlooked detail in the Roman mixing process, a detail so counterintuitive it was hidden in plain sight for 2,000 years. For decades, the CaSH crystals were seen as the final answer. Scientists, armed with modern microscopes and chemical analyzers, peered into thin slices of Roman concrete. They mapped the intricate, interlocking lattice of these calcium-aluminum silicate hydrate crystals. This was the tangible proof of the pozzolanic reaction, the durable matrix that gave the material its strength. It was a satisfying discovery that seemed to close the case. If you could replicate this crystal structure, you could replicate Roman durability. But a quiet, persistent anomaly kept appearing in the data, a clue that the full story was not yet on the table. While the CaSH framework was indeed robust, the analyses revealed something unexpected within the ancient samples. Scattered throughout this crystalline network, like strange, layered inclusions, were other minerals. One in particular, a form of calcium aluminate silicate, seemed almost out of place. Its structure was different, more plate-like and less interlocking. For a long time, it was considered a curiosity, perhaps a minor byproduct of the initial mix, or even a sign of a less-than-perfect reaction. It did not fit the neat model of a uniform, monolithic crystal structure. This was the subtle flaw in the 20th century understanding. Researchers had identified the major players, the backbone of the concrete, but they had catalogued these other minerals as passive spectators. The assumption was that once the concrete set, its chemical life was essentially over. The CaSH crystals were formed, and that was that. The material would then simply endure, passively resisting the elements through its inherent stability. Yet this passive model could not explain the active, almost biological behavior of the Roman harbors. It could not account for the concrete's documented ability to seal its own cracks over time, a property no modern concrete possesses. If the chemistry was finished after the initial cure, then any new crack would be a permanent wound, a gateway for corrosive seawater. But the archaeological evidence was undeniable. Cores drilled from the heart of 2,000-year-old piers showed fractures that had been filled in with new, pristine material, even far from the surface. This was not passive endurance, this was active repair, so the mystery shifted from the macro to the microscopic. The secret to this self-healing capability had to be hidden within the concrete's complex inner architecture, within those very mineral inclusions that science had previously dismissed. The true genius of the Roman recipe was not just in what it created initially, but in what it left deliberately unfinished, a reservoir of potential waiting within the stone. The key to unlocking the final secret lay not in seeing the concrete, but in seeing through it. For centuries, analysis was limited to what could be observed with optical microscopes or inferred from bulk chemical tests. This was like trying to understand a masterpiece painting by looking only at its frame. The intricate, nanoscale architecture within the mortar, the very arrangement of atoms that dictated its behavior, remained a blur. The turning point arrived with a new generation of analytical tools, instruments of such precision they could map a material's inner world. Scientists turned to synchrotron-based X-ray microdiffraction. Imagine a light source millions of times brighter than the sun, capable of producing an extremely focused, high-energy X-ray beam. By aiming this atomic-scale spotlight at a speck of 2,000-year-old mortar, researchers could do something extraordinary. They could not just identify what minerals were present, but could determine their exact crystal structure, their orientation, and even the subtle strains within their lattices. It was like being given a geological X-ray vision. Paired with this was Raman spectroscopy, a technique that uses laser light to probe molecular vibrations. Every mineral, every chemical bond vibrates at a unique frequency. By shining a laser on the sample and analyzing the scattered light, scientists could get a precise molecular fingerprint of the material, identifying compounds too small or too intermixed to see with any other method. This was no longer broad-stroke chemistry. This was forensic analysis at the scale of a billionth of a meter. For the first time, researchers could move beyond cataloging the components of Roman concrete and start to understand their relationships. They could map where one crystal ended and another began, trace the chemical pathways that minerals had taken over centuries, and observe the interfaces where different phases met. This nanoscale cartography revealed a landscape far more complex and dynamic than anyone had presumed. The concrete was not a static, finished product. It was a slow-motion chemical ecosystem. Those strange, plate-like minerals that were once considered curiosities were now visible in stunning detail, and their position within the crystalline network told a new story. They were not flaws, they were features, deliberately engineered reservoirs of potential. This technological leap transformed the mystery from a historical question into a solvable materials science puzzle. The tools finally existed to read the concrete's own diary, written in the language of atoms and recorded over 2 millennia. What they began to decipher would completely rewrite the recipe for eternal stone. Deep within the ancient mortar, the X-ray spotlight revealed a stunning geological guest. Scattered like tiny, pearlescent plates amidst the more common crystalline web were distinct formations of a mineral called aluminum-rich Tobermorite. To a materials scientist, this was like finding a snowflake in a desert. This specific form of Tobermorite is a mineral known to form naturally, but only under conditions of extreme heat and pressure, deep within the Earth's crust or in the throes of a hydrothermal vent. It is a creature of geology, not of human construction. It simply does not belong in a block of concrete that cured at the cool, ambient temperature of seawater. Its presence there was a profound anomaly, a clear signal that the chemical story inside this 2,000-year-old mix was far more complex than a simple pozzolanic reaction. This wasn't a flaw or a contaminant. The crystals were too perfectly formed, too intentionally integrated into the fabric of the material. They appeared as bright, layered inclusions in the scans, often situated at the boundaries between the volcanic ash particles and the binding matrix. Their structure is unique, composed of sheets of calcium, oxygen, and silicon, with aluminum atoms seamlessly substituted into the lattice, making it exceptionally strong and stable. Finding it here meant one incredible thing. The Roman concrete recipe had somehow, and quite accidentally, recreated the intense, transformative conditions of a geological process within a man-made mixture, all at room temperature. The slow, centuries-long conversation between the lime, the ash, and the seawater had built not just a sturdy material, but a miniature, self-contained rock-forming environment. The aluminum Tobermorite was the crystalline signature of that environment, the ultimate proof that this concrete was not merely inert stone. It was dynamically evolving, and this rare mineral held the key to its legendary resilience. This discovery turned the entire narrative on its head. For all of modern history, seawater has been the sworn enemy of concrete. Every engineer's manual, every builder's code, treats saltwater as a corrosive agent to be repelled, sealed out, and battled with protective coatings. The entire goal has been to create a barrier to keep the destructive chemistry of the ocean at bay. Yet the aluminum Tobermorite crystals told a different story. They were not forming in spite of the seawater, they were forming because of it. This led to a radical, almost heretical hypothesis. What if the Romans did not just tolerate seawater in their mix? What if they deliberately used it as the final, crucial ingredient in their recipe? The evidence was pointing to a truth that defied centuries of engineering dogma. Seawater was not the destroyer, it was the catalyst. Think of it this way. The traditional pozzolanic reaction we discussed earlier is like starting a campfire. You combine your fuel, the volcanic ash, with your spark, the lime putty, and you get a good, steady burn that produces warmth and light, the CaSH crystals that give the concrete its initial strength. But if you leave that fire alone, it will eventually consume its available fuel and burn down to embers. Now, imagine if you could design a fire that, instead of dying out, learned to feed on the rain. That is essentially what the Roman concrete did. Seawater, with its rich cocktail of dissolved salts, particularly magnesium, potassium, and chloride ions, did not extinguish the chemical reaction. It evolved it. When seawater infiltrated the porous concrete over decades, it did not initiate a destructive attack. Instead, it provided a fresh stream of chemical reactants. The highly alkaline environment left over from the lime acted as a filter. As the salt water percolated through, it would slowly dissolve more silica and alumina from the volcanic ash particles, much like water filtering through coffee ground. But then, the dissolved magnesium in the seawater would react with this silica-rich solution. This reaction is key. It lowers the overall alkalinity of the concrete's internal environment. And in this new, slightly less alkaline chemical landscape, the conditions become perfect for something extraordinary to happen. The calcium-aluminum silicate hydrate crystals, the CaSH, begin a slow transformation. They start to reconfigure themselves, incorporating more aluminum and reorganizing into that far more stable, plate-like structure, the aluminum-rich Tobermorite. This is not a fast process. It is a geological timescale event happening inside a man-made block. The seawater, by gradually altering the internal chemistry, triggers a long-term maturation. The concrete does not just sit there, it slowly ripens. It becomes more crystalline, more ordered, and significantly more resistant to physical stress and chemical attack. The very salts we spend fortunes to keep out were the essential minerals that guided this final, perfect crystallization. So the harbor blocks were not merely submerged. They were perpetually bathing in the chemical bath they needed to reach their ultimate state of strength. The ocean was not a foe pounding at the gates. It was the silent partner in the workshop, patiently completing a reaction the builders had only begun. But even this elegant theory of seawater as a catalyst faced a stubborn contradiction. If the mixture was so perfectly balanced, why did samples from the most durable Roman harbors consistently show what looked like glaring flaws? For over a century, archaeologists and materials scientists examining cores from these ancient structures had noted them. Tiny, bright white specks no larger than a grain of rice scattered throughout the gray matrix of the mortar. These were lime clasts, little lumps of unreacted or poorly reacted calcium carbonate. To the modern eye, trained on the homogenized perfection of industrial concrete, these inclusions were a sign of failure. They suggested careless mixing, inconsistent batches, a primitive technology that had not yet mastered the art of a smooth, uniform blend. They were the textbook definition of a defect. In modern concrete, such a flaw would create a weak point, a site where cracks could easily initiate and propagate. It was the final, puzzling piece of evidence that seemed to undermine the entire narrative of Roman sophistication. How could a material so carefully engineered for eternal life contain such obvious fundamental mistakes? The answer, when it finally came, was a stunning lesson in humility. The flaws were not mistakes at all. They were the masterstroke. For decades, the lime clasts were catalogued and then ignored, an embarrassing footnote in an otherwise impressive material. But the new generation of researchers, armed with those powerful nanoscale imaging tools, decided to look at these supposed defects not as failures, but as features. They applied their synchrotron X-rays and electron microscopes not to the perfect gray mortar, but directly to these tiny white specks, and most importantly, to the boundary where the speck met the surrounding concrete. What they found there rewrote the recipe. The lime clasts were not inert lumps, they were dynamic chemical reservoirs. The analysis revealed that these clasts had a unique crystalline structure. They were not the fully slaked lime putty used in the initial mix. Instead, they were often composed of quicklime or calcium oxide, the highly reactive, unslaked powder that is the direct product of burning limestone. This was a revelation. It meant the Roman builders were not simply mixing a pre-made lime putty with ash and water. They were using a technique called hot mixing. They were combining the volcanic ash and the coarse aggregate with the dry, powdered quicklime itself, and then adding seawater all at once. Think about the chaotic chemistry of that moment. When quicklime meets water, it undergoes a violent exothermic reaction, releasing a tremendous amount of heat. The entire mixture would have been a churning, steaming cauldron, its temperature soaring. This was not a calm, controlled process. It was a deliberate, engineered chaos. The benefit was twofold. First, the intense, localized heat from these reactions helped accelerate the initial pozzolanic setting process, allowing the massive harbor blocks to achieve early strength even in the cool seawater. But the second, and far more important, function was long-term. Not all of the quicklime would react immediately. Tiny, protected nodules of it would become encapsulated within the hardening mortar, sealed away like chemical time capsules. These are the lime clasts we see today. For centuries, they sat dormant, but when the concrete eventually developed a crack, allowing new seawater to seep in, these clasts sprang to life. The water would reach the quicklime, triggering a delayed slaking reaction right at the site of the damage. This reaction produces calcium-rich, highly alkaline solutions that can flow into the crack. There, they encounter dissolved silica and alumina from the ash, or ions from the seawater, and they precipitate out as new calcium-aluminum silicate hydrate crystals, effectively gluing the fracture shut. The flaw was a self-healing mechanism. The Romans had not achieved a perfect monolithic material. They had engineered a smart one. They built in a distributed network of repair kits, microscopic nodes of potential energy waiting for the signal of damage to activate. What we dismissed as sloppy mixing was, in fact, a brilliantly sophisticated insurance policy, written in chemistry and paid out over millennia. The concrete was not just durable. It was alive with possibility. This chaotic, high-temperature process was not an accident of primitive methods. It was a deliberate, calculated technique we now call hot mixing. Picture the scene at a Roman harbor construction site. Workers would have prepared massive wooden forms, positioning them in the shallow coastal waters where the breakwater was to rise. Nearby, kilns would be burning limestone into quicklime, a process requiring immense heat and careful management. Instead of patiently slaking all this quicklime with water first to make a smooth putty, the Roman builders took a radically different approach. They would take the dry, caustic quicklime powder, still hot from the kiln, and combine it directly with the volcanic pozzolana ash and the coarse aggregate of rock and brick. Then they would add seawater. The moment the water hit the quicklime, the mixture would erupt. A violent chemical reaction, known as slaking, would release a surge of intense heat, easily pushing the temperature of the entire mass well past the boiling point. The wooden forms would likely steam and hiss as this semi-liquid rock churned within them. To a modern engineer, this would look like a disaster, a recipe for explosive cracking and inconsistent material. But the Romans were not creating a uniform paste. They were engineering a dynamic, self-contained ecosystem in stone. The key outcome of this thermal chaos was the creation of those lime clasts. In the turbulent, high-temperature environment, not all of the quicklime could react fully with the water. Tiny, protected nodules of it became encased within the rapidly setting ash and aggregate matrix. Think of them not as lumps but as sealed chemical batteries. They are composed primarily of calcium oxide, a substance with a powerful, latent desire to react. For decades or even centuries after the concrete hardened, these clasts would sit dormant, their potential locked away. They became a distributed network of repair kits, embedded throughout the entire structure. This design is profoundly different from our modern approach. We strive for perfect homogeneity, where every cubic inch of concrete has identical properties. The Romans embraced a form of engineered heterogeneity. Their concrete was a composite material on a microscopic scale, with a strong, durable background matrix punctuated by these highly reactive, strategic inclusions. The lime clasts are the most brilliant flaw in engineering history. They represent a concession that damage is inevitable, and instead of trying to build a wall that never cracks, which is impossible, they built a material that knows how to heal itself. The hot mixing process was the essential first step that made this lifelong repair capability possible. It was the act of planting the seeds that would only germinate when the concrete was most in need. The cracks themselves become the trigger for repair. Imagine a tiny fissure, no wider than a hair, forming in the concrete after centuries of pressure. In any modern structure, this is the beginning of the end. Salt water seeps in, finds the steel, and begins its corrosive work. But in the Roman design, that same infiltration of seawater sets a completely different chain of events into motion. The water travels along the crack until it encounters one of those white lime clasts, a sealed pocket of pure chemical potential. Upon contact, the water immediately begins to dissolve the outer layer of the clast. This isn't a destructive process, it is an activation. The dissolving clast releases a concentrated, calcium-rich solution, highly alkaline, that flows directly into the open space of the fracture. This solution is now swimming with the very ions that were carried in by the seawater dissolved silica, alumina, magnesium, and potassium. In this confined, chemically rich environment, something beautiful happens. The dissolved elements begin to recombine. New crystals start to form, not randomly, but preferentially on the walls of the crack itself. These are primarily calcium-aluminum silicate hydrate minerals, the same family that gives the concrete its backbone, but now being grown in situ, like a geological scar tissue. The process is slow, patient, and utterly autonomous. Over months or years, the fissure is gradually filled from the inside out, not with a foreign patch, but with a perfect mineralogical continuation of the original material. The crack is not just covered up, it is literally stitched back together at a molecular level, becoming, in time, as strong or even stronger than the surrounding matrix. This is why cores from the heart of these ancient piers show fractures that have been completely healed, filled with pristine, crystalline material that is chemically identical to the mortar around it. The concrete possesses a form of mineral memory. It remembers its original recipe and, when damaged, uses the ingredients provided by the sea to mix a fresh batch of glue in the exact spot it is needed. The system requires no human intervention, no maintenance crews, no epoxy injections. It is a closed loop of resilience where the cause of damage in other materials becomes the catalyst for regeneration in this one. The harbor does not just withstand the sea, it learns from it and uses its endless energy to perpetually renew itself. This fundamental difference in philosophy is crystallized in the mixing process itself. Roman builders created their concrete through hot mixing, a dynamic, almost volcanic event that embedded future potential directly into the material. Modern Portland cement, by contrast, is the product of cold mixing, a controlled, industrial procedure designed for uniformity and immediate stability. The two methods could not be more opposed in their goals and their outcomes. The Roman process begins with quicklime, a powder so reactive it heats water to a boil upon contact. Combining this with volcanic ash and seawater creates a churning, high-temperature reaction that traps unreacted lime clasts within the hardening mass. The result is a deliberately heterogeneous material, a complex mosaic of different crystalline phases and reactive pockets. It is engineered not to be perfect from day one, but to be adaptable. Its chemical story is left deliberately unfinished, with characters like the lime clasts waiting in the wings for their cue to enter the stage centuries later. This concrete is designed to evolve, to converse with its environment, and to use the passage of time as a tool for strengthening. It is a material built with patience for patience. Modern concrete follows an entirely different script. Portland cement is manufactured by superheating limestone and clay in a rotary kiln, then grinding the resulting clinker into a fine powder. This powder is highly processed and homogeneous. When mixed with water and aggregate at a job site, the process is calm and controlled. The goal is a smooth, uniform paste that sets predictably into a rigid, monolithic solid. Every batch is tested to be chemically identical, with no unexpected inclusions or reactive surprises. This material is designed to be inert and static from the moment it hardens. Its chemical life is meant to be brief and complete. Any subsequent change, like the infiltration of seawater or the corrosion of steel, is not part of the plan. It is a catastrophic failure of the design. We build for a finished product, a static object that we hope will resist all forces unchanged. The Romans built for a living process, a material that would mature and adapt. One philosophy sees time as an enemy to be held at bay. The other enlisted time as a silent co-builder. This is why our harbors face a scheduled decay, while theirs discovered a pathway to perpetual repair. The most compelling validation of this self-healing property comes not from a laboratory, but from an ancient text, centuries before our electron microscopes could map a crystal lattice. A Roman scholar and naval commander named Pliny the Elder observed the same phenomenon with his own eyes. In his monumental encyclopedia, Naturalis Historia, a work intended to catalogue all the knowledge of the natural world, he turned his attention to the harbors dotting the empire's coast. Writing about the concrete used in maritime structures, he made a specific and astonishing note. He described how these mixtures, once poured into the sea, unite to become, in his words, a single stone mass impregnable to the waves. This is not a poetic flourish. It is a precise technical observation from a man renowned for his relentless curiosity. Pliny did not have the vocabulary of calcium aluminate silicate hydrates or aluminum-rich Tobermorite. What he saw was the effect. He witnessed the transformation of a poured slurry into a unified, monolithic rock. More importantly, he identified the catalyst. He explicitly credited contact with seawater as the agent that achieved this final, indestructible state. His word, impregnable, speaks directly to the outcome of that slow chemical maturation. The waves could not break it down because the material had become something more than the sum of its parts, a geological entity forged by the sea itself. This historical account is not a vague legend. It is a first-hand corroboration of the very process modern science has only recently decoded. Pliny's observation bridges two millennia, connecting the empirical knowledge of the Roman builders with the analytical proof of 21st century research. He confirms that the durability was not an accidental quality, but a known and celebrated feature of their technology. The builders understood the result, even if they did not grasp the nanoscale mechanics. They knew that their concrete needed the sea to fulfill its ultimate purpose, to achieve that legendary unity and strength, so we are left with a powerful convergence. The white lime clasts seen under a microscope, the aluminum-rich Tobermorite crystals identified by X-ray diffraction, and the 2,000-year-old testimony of a Roman naturalist all tell the same story. It is a story of a material designed not to resist its environment, but to collaborate with it, to use the relentless energy of the ocean as the final, patient craftsman in its own perfection. Pliny's observation reveals a profound truth about Roman engineering. It was not a science of abstract formulas, but a technology of observed results. They perfected this concrete recipe through a process spanning generations, a slow accumulation of practical wisdom passed from builder to builder. They had no concept of atoms, no periodic table, no understanding of ionic bonds or crystalline lattices. What they possessed was something equally powerful, meticulous, and relentless observation. They saw that a certain volcanic ash from Pozzuoli, when mixed with lime and seawater, produced a mortar that grew harder in the ocean. They noted that using quicklime directly created a hotter, more durable mix. They witnessed the final, unified stone mass that Pliny described. They did not know why it worked. They only knew through centuries of trial and error that it did. This is engineering without calculus, materials science without microscopy. It is the triumph of empirical knowledge, of learning the rules of the world by carefully watching its behavior. Think of it as mastering a complex recipe without ever learning the chemistry of cooking. A master baker knows that combining flour, water, yeast, and salt in a specific way with precise timing and temperature yields perfect bread. They may not understand the molecular activity of gluten formation or the metabolic processes of fermentation, but through repeated practice and subtle adjustment, they achieve a sublime result. The Roman builders were the master bakers of the ancient world. Their recipe for opus caementicium was the product of a long, unbroken dialogue with their materials. A failed harbor wall in one city taught a lesson that informed the success of the next. A batch that crumbled in fresh water highlighted the necessity of salt. This knowledge was hard-won, embedded in practice rather than in theory. It was a living library of techniques, written not on scrolls but in the very structures that lined their coast. This empirical path led them to a stunningly sophisticated chemical outcome. They engineered a self-healing material, a substance that could reconfigure its own atomic structure over centuries, all while believing they were simply making a better kind of stone. They manipulated nanoscale reactions without a nanometer in sight. They created aluminum-rich Tobermorite, a mineral that forms deep within the earth, on a harbor floor using only buckets, shovels, and keen eyesight. This gap between their understanding and their achievement is perhaps the most humbling part of the story. It asks us to reconsider what true knowledge looks like. Can a civilization know a thing deeply, use it masterfully, and yet remain completely unaware of the fundamental principles governing its behavior? The Romans answered with a resounding yes. Their harbors stand as monuments not to theoretical science, but to the profound power of paying attention, of learning from failure, and of trusting the evidence of the material world over the elegance of an untested idea. Their legacy is a challenge to our own age of hyper-specialization, reminding us that sometimes the deepest secrets are not found by looking further inward at equations, but by looking longer and more carefully at the world right in front of us. This ancient wisdom now faces the ultimate test of the modern laboratory. Can we, with our advanced instruments and scientific method, successfully recreate the 2,000-year-old recipe and witness its legendary behavior firsthand? Across the world, in materials science labs, researchers have undertaken this exact challenge, moving from historical analysis to active reconstruction. The process begins with careful sourcing. They acquire volcanic ash from the same regions the Romans used, like Pozzuoli in Italy. They burn limestone to produce quicklime, that reactive, caustic powder. Following the hot mixing method described by Vitruvius and inferred from the lime clasts, they combine the dry quicklime with the ash and aggregate, then add seawater. The mixture immediately comes alive, steaming and heating up, just as it would have on an ancient dock. They cast this churning slurry into small blocks or cylinders, modern analogues of the great harbor piers. But the real experiment begins after the initial set. To test the claims of self-healing and long-term durability, scientists cannot wait for centuries. They use accelerated weathering tests, placing the replicated Roman concrete samples in harsh conditions designed to mimic decades of marine exposure in a matter of months. The samples are subjected to cycles of soaking in saltwater baths, drying, and even mechanical stress to induce controlled cracking. Then, the researchers watch and wait, using their powerful microscopes and sensors to monitor the interior. The results are unequivocal and thrilling. Within these lab-created samples, the same rare aluminum-rich Tobermorite crystals begin to form. Scans reveal the plate-like structures growing at the boundaries between the ash and the matrix, a direct confirmation that the hot mixing process successfully recreates the slow geochemical conditions. Even more dramatically, when the researchers deliberately crack a sample and then expose it to seawater, they document the self-healing mechanism in real time. Over weeks, the cracks begin to fill. Chemical analysis shows the new material sealing the gap is rich in calcium aluminum silicate hydrates, precipitated from the solutions released by the dissolving lime clast. The modern experiment validates the ancient outcome. It proves that the Roman formula was not only effective but reproducible, a reliable technology rather than a lucky accident. This laboratory verification transforms the story from a fascinating historical mystery into a tangible blueprint for the future. We are no longer just admiring a relic. We are holding a working set of instructions written in chemistry and now confirmed by science for building things that last. the implications of this ancient recipe reach far beyond historical curiosity, touching a critical modern challenge: sustainability. While our contemporary world grapples with the enormous carbon footprint of construction, Roman concrete presents a compelling alternative model, one built on lower energy and smarter chemistry. Consider the production of modern Portland cement, the glue of our global infrastructure. Its creation is an intensely industrial affair, requiring limestone and clay to be heated in massive rotary kilns to temperatures exceeding 1,400 degrees Celsius. This process, known as clinkering, is incredibly energy-intensive, relying heavily on fossil fuels. Furthermore, the chemical reaction itself releases carbon dioxide trapped in the limestone, a significant emission on top of the fuel burned. The result is that cement production alone is responsible for roughly 8% of global human-caused carbon dioxide emissions every single year. Now contrast this with the Roman lime production. Their process also involved heating limestone, but the target temperature was far lower, likely around 900 degrees Celsius. This several hundred-degree difference represents a massive reduction in energy demand. Their kilns were simpler, often wood-fired, and while not without environmental impact, the scale and efficiency were orders of magnitude smaller. The material itself tells a story of less processing. Roman concrete used raw volcanic ash, simply dug from the earth and sieved, not subjected to the superheating and fine grinding of modern cement. The aggregate was often rubble from previous constructions or local stone, a form of ancient recycling. Perhaps most strikingly, the Roman formula required no steel reinforcement. The production of steel is another major source of industrial emissions, and its necessity in our concrete creates that fatal vulnerability to corrosion in marine environments. The Roman system eliminated that entire category of material and its associated carbon cost by designing a concrete that was inherently strong and flexible in compression, perfect for the massive, gravity-based structures they built. When you combine these factors, lower firing temperatures, minimally processed natural pozzolans, no steel, and a material that grows stronger with time, you begin to see a blueprint for a different kind of construction philosophy. It is a philosophy of working with geochemistry rather than dominating it with brute force energy. Imagine a future seawall or harbor block that, instead of being a high-emission product with a 50-year expiration date, is made from locally sourced volcanic materials and lime produced with renewable energy. This concrete would not need to be replaced in decades. It would mature and self-repair for centuries, locking away carbon as it continues its slow pozzolanic reaction. The research into Roman concrete is no longer just an archaeological pursuit. It is a forward-looking materials science mission. By decoding this 2,000-year-old technology, we are not looking backward in nostalgia. We are uncovering a potential pathway forward, one that could help build a more durable and less carbon-intensive world. The silent stones in the sea may yet have their most important lesson to teach us. Yet this promising path is not without its own formidable obstacles. Translating a 2,000-year-old triumph into a modern building code involves confronting a series of practical realities that our contemporary world is not yet fully equipped to handle. The first and perhaps most significant hurdle is time itself. Roman concrete did not achieve its legendary strength in 28 days, the standard testing period for modern mixes. Its curing was a slow, patient maturation, a chemical conversation that unfolded over years and decades. In our era of fast-track construction, where projects are measured in months and financial returns are calculated quarterly, a material that asks us to wait for its full potential poses a profound logistical challenge. We have engineered our entire industry around speed, from rapid setting cements to prefabricated components. Adopting a material with a fundamentally different timeline would require a radical rethinking of project schedules, financing models, and even our cultural definition of progress. It asks us to build for the next century, not just the next fiscal year. Then there is the question of certainty, the language of modern engineering. Today, every structural material is governed by rigorous codes and standards. Before a new concrete mix can be used in a skyscraper or a bridge, engineers must have exhaustive data on its precise compressive strength, its tensile strength, its behavior under seismic loads, and its long-term creep and shrinkage. We have over a century of such data for Portland cement concrete. For Roman-style concrete, that database is essentially blank. We have the enduring proof of ancient structures, but translating that proof into the precise, quantifiable numbers required by a 21st-century building inspector is a monumental task. Each new mix, with its specific volcanic ash and lime, would need years of accelerated and real-time testing to generate the confidence curves and safety factors that are the bedrock of modern structural design. Without this codified data, it remains a fascinating laboratory material, not a trusted tool for public infrastructure. The very ingredients that give this ancient concrete its character also introduce a challenge of consistency. The magic of the Roman recipe relied on specific, highly reactive volcanic ashes like the pozzolana from Italy. But volcanoes are not factories. Their ash varies in chemical composition from one eruption to the next, and even from one side of the same deposit to another. This natural variability is the antithesis of modern industrial production, which demands strict uniformity. A construction company in North America or Asia cannot reliably source identical volcanic ash for every project. While there are other natural and even industrial byproducts like fly ash from coal plants that exhibit pozzolanic properties, replicating the exact alchemy that produced aluminum-rich Tobermorite is not guaranteed. This means each potential source material would require extensive characterization and testing, adding cost and complexity where the modern industry values simplicity and repeatability above all. Finally, we must confront the architectural elephant in the room: steel rebar. Our modern world is built in tension. We create soaring, slender structures, vast cantilevers, and complex shapes that rely entirely on the tensile strength of embedded steel. Roman concrete, in its pure form, is a material of magnificent compression. It excels at being squeezed, at bearing massive weight, as in a dome or a thick seawall. But it has little innate resistance to being pulled apart. The Roman solution was architectural, using arches, vaults, and thick walls to channel all forces into compression. Our solution for the last century and a half has been chemical and metallic, pouring concrete around steel to handle the pull. Simply removing the rebar from our current construction paradigm is not an option. It would mean redesigning our entire architectural language from the ground up. The dream of a corrosion-proof, marine-grade concrete is tantalizing, but it must somehow find a way to coexist with the steel-dependent skeletons of our cities, or inspire a completely new form of building that returns to those principles of mass and form. The ancient harbor does not just offer us a new recipe, it quietly questions the very foundations of our modern built environment. Yet the story of Roman concrete does not end at the water's edge. If the secret truly lay in a unique chemical packed with the sea, then a glaring question arises: what about their most famous structures on land? The Pantheon in Rome, with its vast, unreinforced concrete dome, has sheltered the city's heart for nearly 2,000 years. It has endured earthquakes, fires, and the relentless weight of its own mass without the constant bath of seawater. Its survival challenges the narrative, forcing us to ask if the marine concrete's magic was a special case, a happy accident for harbor builders, or evidence of a far deeper Roman philosophy of material endurance. To find the answer, we must look up into the very fabric of the dome itself. The Pantheon is a masterpiece of architectural engineering, a perfect hemisphere of concrete spanning 142 feet, a record it held for over a millennium. Its builders faced a monumental challenge: how to construct a dome of such immense scale that would not collapse under its own weight. Their solution was a breathtaking exercise in material optimization. They did not pour a uniform, homogeneous mass. Instead, they graded the concrete with meticulous intelligence. At the heavy, supporting base of the dome, the aggregate is dense travertine and brick. As the dome curves upward, the mix changes. The builders gradually lightened the load by using progressively lighter aggregates, switching to porous volcanic stones like tuff and pumice at the very top, around the iconic oculus. This is not random. It is a calculated strategy to reduce stress where it matters most, but the grading speaks to more than just weight distribution. It reveals a sophisticated understanding of their materials' properties. Different aggregates interacted with the lime and ash mortar in subtly different ways, affecting setting time, strength, and even thermal expansion. The Pantheon's concrete is a composite material engineered in layers, each chosen for its role in the structural symphony. This alone suggests a knowledge that transcended simple recipe following. They were tailoring their concrete to its specific duty, a concept at the very heart of modern material science. So, while the dome never knew seawater, it benefited from the same core technological wisdom, the pozzolanic reaction. The mortar binding those graded aggregates was made with the same volcanic ash, the same lime, mixed with fresh water. The resulting calcium-aluminum silicate hydrate crystals formed the same strong, interlocking matrix. The absence of seawater simply meant the concrete followed a different, slower path of maturation. Without the magnesium and other ions from the ocean to catalyze the formation of aluminum-rich Tobermorite, the terrestrial concrete matured into a different, yet still exceptionally durable, crystalline form. The self-healing mechanism, however, would have been different. Without the constant reservoir of seawater, the lime clasts embedded via hot mixing would have remained mostly dormant. Their repair function would have been triggered not by the sea, but by rain. The occasional infiltration of rainwater through the dome's surface or microcracks from thermal expansion could have dissolved these clasts, allowing for localized healing over centuries. The environment was less aggressive, so the material's long-term needs were different. The Pantheon did not need to perpetually regenerate against a corrosive foe. It needed to settle, stabilize, and bear immense compressive weight forever. And it has. The key insight is that the Roman builders were not relying on a single, universal concrete. They were masters of a flexible, adaptable technology. For the harbor, they designed a concrete that collaborated with a hostile environment, using seawater as a chemical partner. For the dome, they designed a concrete optimized for pure structural mass and stability, using graded aggregates to manage physical forces. In both cases, the foundational principle was the same: a deep, empirical understanding of how their three simple ingredients, lime, ash, and aggregate, could be manipulated to converse with their environment, whether that environment was the pounding sea or the silent, immense force of gravity. The harbor concrete reveals a dialogue with chemistry. The Pantheon reveals a dialogue with physics. Together, they show that Roman mastery was not about one secret ingredient, but about a holistic philosophy of building in conversation with the world. This raises a final, profound thought. If they applied such nuanced understanding to different structures, what other subtleties of their material science have we yet to uncover, hidden in the mortar of a forgotten wall or the foundation of a fallen bridge? Their legacy is not a single answer, but a method of asking the right questions of the very earth they built upon. The Pantheon's silent endurance reminds us that for all we have decoded, significant shadows still linger around this ancient craft. Our modern understanding, built on electron microscopes and chemical analysis, gives us a powerful but incomplete picture. We can replicate the mix, we can observe the self-healing in a lab, but we cannot fully reconstruct the mindset of the Roman builder standing on a wooden form, watching his steaming creation settle into the waves. This gap in knowledge holds some of the most intriguing remaining mysteries. First, consider the question of quality control. We know the recipe from Vitruvius, but a recipe is not a guarantee. How did they ensure consistency across an empire, from the shores of Britain to the harbors of Egypt? There were no standardized testing labs, no compression strength machines. Their methods were almost certainly empirical and sensory. A master mason might judge the quality of lime by its heat upon slaking, or the fineness of volcanic ash by its feel between his fingers. The setting time and workability of a batch would have been learned through a lifetime of tactile experience, knowledge passed down not through manuals, but through the mentorship of the worksite. This reliance on human judgment introduces fascinating variables. Could a particularly skilled crew in one province produce a concrete that was subtly superior to another's? Were there regional variations in technique, small tweaks and local secrets that have been completely lost to history, leaving their signature only in the varying durability of ruins we have yet to compare side by side? Then there is the mystery of material sourcing. We focus on the famous pozzolana from Pozzuoli, but the Romans built with concrete across vast territories, many far from that specific volcano. Did they discover and utilize other volcanic deposits with similar reactive properties? Archaeologists have found evidence of concrete using ash from German and Turkish volcanoes. Were these materials considered perfect substitutes, or were they chosen for different applications, perhaps where a slightly slower set or a different color was desired? The Roman network of trade and engineering was unparalleled. It is entirely plausible that they categorized different ash sources, much like a modern winemaker understands different terroirs, each lending a unique characteristic to the final product. This leads to the deepest and most philosophical mystery of all. To what extent did the Romans comprehend the long-term chemical processes they had set in motion? Did they understand that they were engineering a material that would not just last, but actively improve for centuries? Pliny's observation suggests they knew the seawater was essential for the final, unified stone. But did they grasp that this was because of a slow, crystalline transformation, or did they see it as a kind of mystical petrification? Their knowledge was profoundly practical. They knew that if you followed these steps, you got this magnificent result. But the line between seeing a correlation and understanding a causation is vast. Perhaps the most compelling possibility is that they operated with a different kind of understanding, one rooted in a world where materials had vital properties and interactions with elements like water and earth were part of a living dialogue. In their framework, the concrete wasn't just hardening, it was achieving its proper state, its final unity with the natural world. This perspective, so different from our reductionist science, may have been the very thing that allowed them to accept and harness a process whose full timeline stretched far beyond a single human life. They built for the gods, for the empire, for eternity, concepts that inherently demand a patience we have largely abandoned. So as we peer into their mortar with our advanced tools, we are left with a humbling realization. We may have mapped the crystalline structure of their concrete, but we are still deciphering the architecture of their thought. The true recipe was not just lime, ash, and water. It was a combination of empirical observation, patient tradition, and a cultural willingness to build legacies rather than just structures. What other silent dialogues between material and maker are waiting to be heard in the stones they left behind? The silent dialogue between Roman concrete and the sea reveals a complete architectural philosophy. This investigation has shown that their material's immortality was no accident, but the product of a brilliant synergistic system. Three key elements worked in concert: reactive volcanic ash, a hot mixing process that embedded self-healing lime clasts and the catalytic power of seawater itself. Alone, each piece is interesting. Combined, they form a chemical symphony that plays out over centuries. The ash provided the silica-rich fuel. The hot mixing planted the reactive seeds for future repair. And the ocean, far from being an enemy, became the perpetual chemical bath that guided the concrete's slow, perfect crystallization into a form of artificial rock. This was not a material designed to remain unchanged. It was engineered to evolve, to improve, and to heal. Its strength was not locked in at the moment of pouring. It was a potential that unfolded through time, using the very forces that destroy our modern structures as its essential partners. The lesson here transcends ancient history. It challenges a fundamental assumption of our industrial age, the pursuit of static perfection. We engineer materials to be finished, to resist all change. The Romans engineered theirs to be adaptable, to welcome certain changes as a path to greater resilience. They built with an understanding that time could be an ally, not just a force of decay. Their harbors ask us to reconsider what we mean by a durable design. Is it something that resists its environment at all costs, or something that learns to collaborate with it, to find strength in the dialogue? As we face our own global challenges, from crumbling infrastructure to the environmental cost of construction, this 2,000-year-old wisdom feels startlingly urgent. It suggests that sometimes the most advanced solution is not the newest, but the one that has already stood the test of millennia. So the next time you see a modern seawall being repaired or a bridge closed for maintenance, let your mind wander to those quiet blocks submerged in the Mediterranean. They are more than ruins, they are a living question. What other forgotten technologies, what other conversations with the natural world might be waiting in the pages of history, holding elegant answers to the problems we consider unsolvable today?